we're going to move right into the second law of thermodynamics. If you're following the 10th edition, this is going to be chapter 6. If not, it'll be somewhere similar, as they all flow pretty much together. Here are the objectives. We're not going to run through each one, but of course we're going to go over what the second law of thermodynamics is and just some things that accompany that. So for the second law of thermodynamics, we talked about it in the first lecture, where the biggest contribution that the second law did was the arrow of time, or some people say the arrow of time. And we often actually use statements to describe the second law of thermodynamics because, in my opinion, it's not as straightforward as the 0th law or the first law. So remember the 0th law, that's basically where we got temperature measuring, right? No matter where you are on Earth, water is going to freeze at 32 degrees. And when you have that third item, you can, measure and verify that. And the easiest way to think of that third entity or that third body in the 0th law is a thermometer, right? And then the first law, we just spent 5 chapters learning about it. That's energy can never be created nor destroyed. It can only be transferred or changed from one state to another, or from one, whether it be potential energy, it can go to kinetic energy, things like that. So now we have the second law. And so this is that arrow of time. And you've heard me mention the apple example, right? If you have apples, it's going to rot, right? You're never going to witness it go from rotting to unrotting, right? So just like here, a cup of hot coffee does not get hotter in a cooler room, right? Transferring heat to a wire will not generate heat, okay? Transferring heat to a paddle wheel will not cause it to rotate. Just because you can transfer heat and that paddle wheel will get energy, that doesn't mean that it's going to result in it rotating. These processes cannot occur even though they are not in violation of the first law, right? They're not violating the first law at all. Energy can never be created nor destroyed. It can only be transferred. Well, we are definitely transferring heat to a paddle wheel, but that's not going to cause it to rotate, right? Transferring heat to a wire will not generate electricity, okay? This is that arrow, okay? One way. Processes occur in a certain direction and not in the reverse direction. So here are these processes. So within these processes, so you have a process that's going through, and you see you have first law, and then second law, sorry. And a process must satisfy both the first and second laws of thermodynamics to proceed. And it has to go in one way, right? So you have to have an energy transfer, right? And then it needs to satisfy that the process occurs in a certain direction and not in the reverse direction. So here's the major uses of the second law. A second law may be useful to identify the direction of a process, right? We've talked about that quite a lot. The second law asserts that energy has quality. We talked about that just a little bit. And we talked about it under the curve, right, in the two-phase, what that quality is. So the second law asserts that energy has quality as well as quantity. So we've measured the amount of energy, but now we're going to talk about the quality of it. The first law is concerned with the quantity of energy and the transformations of energy from one form to another, with no regard to its quality. The second law provides the necessary means to determine the quality, as well as the degree of degradation of the energy during a process. So that's when we can start talking about how that energy is degrading, right, through a process. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems, such as heat engines, refrigerators, as well as predicting the degree of completion of chemical reaction. Right? So if we're talking about calculating the amount of energy, we can definitely do that. We can calculate with no limit. We can calculate to infinity, right? You can calculate as high as you want, or you can calculate chemical reactions in an endless amount. But when you start talking about the degradation of that chemical, right? Or the degradation of the heat engine and the refrigerators with the refrigerant, things like that. That's when you start looking at, oh, okay, well, we can't really calculate to infinity because it's not theoretically possible to have infinitely usable refrigerant in a refrigerator, right? Or infinite amounts of hydrogen and oxygen to mix it. So it takes into account what degrades during a process so that you can know what the maximum life of that process can be. A hypothetical body with a relatively large thermal energy capacity, mass times specific heat, that can supply or absorb finite amounts of heat without undergoing any change in temperature is called a thermal energy reservoir, or just a reservoir. So that was a lot in practice, right, in the real world, where feel like it's easier to understand. Large bodies of water, oceans, lakes, rivers, as well as the atmospheric air, can be modeled accurately as thermal energy reservoir because of their large thermal energy storage capabilities, or thermal masses, right? So we talked about that a little bit. If you go and take the temperature of a body of water, right? And you have someone boiling water 10 feet from you or 20 feet from you in the ocean, that ocean is going to be able to absorb that and likely not even change what you're able to measure in that large body of water. Bodies with relatively large thermal masses can be modeled as thermal energy reservoir because it can hold, it can accept, it can absorb that thermal energy. A reservoir that supplies energy in the form of heat is called a source, okay? And one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat, okay? So you see that thermal energy source pushing that heat out, and then you see the thermal energy sink receiving that heat in. A source supplies energy in the form of heat, and a sink absorbs it. So you can think of, if it's easy for you, like a faucet, right? Thermal energy source is going to provide it. That's the faucet. And then the sink is going to receive that heated water. Heat engines, device that converts heat to work. We just talked about that in the first slide here when we said, hey, you can give something all day heat. That doesn't mean that it is going to spin the turbine, right, or spin the shaft. Well, here you go. You've got a heat engine, a device that converts heat to work. Because you can give energy. Energy can be transferred through two different means, heat and work. Heat transfer and work, right? It's the two ways we transfer energy. But sometimes we have a lot of heat, like the sun. Sometimes we have a lot of heat, but you know what I need? I need my car to go. I need my tires to spin. I need work being done. I don't need any more heat. I need work. But all of our energy originates from the sun, originates from heat. So you can look at all of our work being done in non-natural forms. So you could make the argument that, you know, like a waterfall can produce work, right? Things like that. But when you're talking about heat from a sun, you know, from a fire, things like that, that you're basically converting it to work, right? They receive heat from a high temperature source, solar energy, oil furnace, nuclear reactor. They convert part of this heat to work, usually in the form of a rotating shaft. That's by and large what we use because it's simple, it's long lasting, and it's one of the more efficient ones that we have. They reject the remaining waste heat to a low temperature sink, the atmosphere, rivers, things like that, that can absorb it. And they operate on a cycle, right? In a cycle, think of a clock. You start at 12, you end at 12. And not just that you end at 12, but that you have made it all the way back, right? With no change cycle. Work can always be converted to heat directly and completely, but the reverse is not true, okay? That's very important for the second law of thermodynamics. Remember, we have an arrow. So think of this arrow. Work can be converted to heat directly and completely, but the reverse is not true, okay? So you see work in the water going to heat, and then you see heat going into the water. That doesn't mean you're going to get work, right? They're not interchangeable. They're not exactly the same in reverse, okay? So this is passing the second law of thermodynamics. Some more on heat engines. Heat engines are other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. We have spent a lot of time referring to all of our things, air, water, you know, things like that as working fluids. Okay, so you see that high temperature source, right? And so we're going to come down and we're going to get work out. That high temperature source is spinning a shaft, maybe right here in the middle. Right here, we've got like a little fan blade in here, a little turbine, and it is spinning that shaft and we are getting work out of it. Work out. Okay, but then the rest of it, we're just going to get some heat transfer and it's going to go into a low temperature sink. And remember, our atmosphere can also serve as a low temperature sink. This is where you get a lot of pollution from before we learned to clean. I mean, it's still happening, but before, you know, by and large, industry knew to clean what you were expelling, right, into these low temperature sinks, into the oceans, things like that. Okay. Qn is the amount of heat supplied to a steam in boiler from a high temperature source, furnace, so it's the heat transfer in. Okay, and then Q out is the heat transfer out, the amount of heat rejected from the steam in condenser to a low temperature sink, the atmosphere or river, things like that. W out is work out, the amount of work delivered by steam as it expands in turbine, right? Because we need an actual device to convert that heat to work. Work in is the amount of work required to compress water to boiler pressure. Okay, so, and then net work is going to equal work out minus work in, and that unit is in kilojoules. Okay, and so then you've got net work out equals Q in minus Q out, kilojoules. It's just the difference between those. But what's really interesting here is the schematic. It's a schematic of a steam power plant. And you'll see that you don't per se have a starting point, but if you follow the energy, you do. So when we've been talking about earlier about just devices, you know, and you have that. The starting point's here and the ending point's here, right? So we have by and large been looking at devices, but the way that I want you to think about here, and the way that hopefully you have been, even just unknowingly, is that you've actually been following the energy or the heat sources. So here, the Q in, this is your starting point. So you've got some heat transfer in, such as a furnace, right? So that's your heat in. It's going to go into a boiler, and then we're following these arrows. And then we're going into a turbine. Into that turbine, we're going to get some work out. Remember, we're getting some work out, and then we're going to expel the rest, the byproduct, okay? We're going to go ahead and throw that into a condenser. That condenser is going to go around. We're also going to have some heat out. We're going to throw some out in the energy sink, such as the atmosphere. But wait, whatever is condensed, we're going to bring back on up. We're going to have some work being put in because remember, a pump is meant and a condenser is meant to reverse, to do the things that we cannot do in nature, like a refrigerator or pump water upstream, things that don't occur naturally. So we're going to put in some work here, some work in to help these things along so that we can have some more byproduct into this boiler, right? So maybe this condenser, maybe the energy sink is being expelled as, whatever kind of working fluid. Maybe it's just, some sort of oxygen, or oxygen mixture, thing like that. But maybe we have a working fluid that's being contained in here in this cycle. You see the cycle? We're back at the boiler. Are we just stopping here? No, we're just keeping going. So this working fluid is just going around, 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 around. It's never ending, theoretically, right? Never ending. The same kind of system that you have every day, and if you may have already been thinking of it right now, is putting oil into your vehicle, right? That oil is theoretically never supposed to leave your car, right? If we could have oil that lasted forever and never needed to be changed, that's the goal. Over, my whole lifetime, we have made large advances. You can go, instead of having to change your oil every 3,000 miles, now you can change it, I mean, it takes long time, thousands of miles, right? So theoretically, if we had an oil that didn't get dirty and a 100% efficient, system within our vehicle, then we would never need to change our oil. And hopefully there would be no leaks, right? Theoretically, no leaks, no friction, no things like that, right? Then it could stay as our working fluid and it could just go in a cycle. This whole time, just keep going around, around, around. Maybe heat that's coming in or heat generated, right, is just expelled as something else, not the oil. Okay, so here's a working of the network. It's just the difference between work in and work out, whichever way you do that, right? And so then this is, you can think of it like self-propelling, right? So you have work out, and that's your network. This is what you're able to keep. This is what is usable. And then you have work that's coming in. We have underneath the hood, you have self-propelling systems. You can think of one, or self-powered systems. You can think of an alternator, right? Portion of the work output of a heat engine is consumed internally to maintain its continuous operation. That's fantastic. It's internally stable. It's internally driven, right? So if you're going to expel out some of that work here, so if you're going to expel out some of this work, we're going to, of course, want to use it. But wouldn't it be great if some of it just went right back around here? And you didn't need another device to come in and put. You didn't need another turbine here. Because how are we getting this work in? It's got to come from somewhere. Well, maybe we can just take some of the work over here. Just put it right into this side, right? That would be great. Thermal efficiency, when we're talking about, transferring heat, well, we want to make it as efficient as possible, because remember, we went over like refrigerators and air conditioners, things like that. We learned that when we say something's efficient on the grand scheme of 100% efficiency, it's definitely not efficient. So we have thermal efficiency, the network output over the total heat input. It's just that ratio. And so we have, remember, N is for efficiency, right? Remember, this is efficiency. And TH, that's not efficiency, that's thermal. Remember, I always have at least one student. It's like 7th, 8th, nth, So you have network out over heat transfer in, and then network out is just the difference between heat transfer in and out, because those, remember, are equal. We learned that in Thermal 1. And then thermal efficiency is 1 less the ratio of Q out and Q in. The fraction of heat input that is converted to network output is a measure of the performance of heat engine and is called thermal efficiency. Of course, we're just going to measure the performance. How efficient is it, right? Some heat engines perform better than others, of course, which means they convert more of the heat they receive to work. For example, how efficient are you at this class or any of your classes? Are you able to look at all of these videos or go to all of those classes? How efficient are you at taking in that information and being able to regurgitate 100% of it? I don't know about you, but I've been in some classes that my efficiency neared 0. I had to put in a lot of work on the outside because in class, maybe it didn't make sense. Maybe it didn't pick up. Maybe I missed a class. My efficiency is going to be 0, right? I'm not going to get any of it. And then some classes, or even some parts of the class, I'm like, oh my gosh, I remember that. I will never forget that. And so my efficiency is 100%. Most people are neither. Most people are not 0. Most people are not 100. You know, my students put in about as much time outside the class as inside to get thermo, because thermo is a very difficult subject. It takes a lot of working in it. It's not something that you can just take in and then regurgitate and spit out. It has to be worked, and that's true for every student that I've ever taught, no matter the GPA or anything. It just takes a lot of work. So you can measure your efficiency, see if your efficiency in this class gets better throughout. All right, QH is the magnitude of heat transfer between a cyclic device and a high temperature medium. So it's TH, okay? So that's high temperature. And then QH is high heat transfer, right? High heat transfer. And then QL is magnitude of transfer between a cyclic device at a low temperature, or TL, right? So you see here, you've got this high temperature reservoir. If you've got high temperature here, you're going to have high heat transfer. And then you're going to have low heat transfer, you're going to have a low temperature right here, TL. Okay, and then through here, you have a heat engine, and you have this little cycle. You see the pump, pump right here. You've got a turbine here, right? Condenser maybe here. And then you have some network out, and then you've got the reservoir. And you've got the definitions and equations that we've gone through. And then here's those formulas again, and it just kind of shows you. So remember, heat is never created nor destroyed, and it needs to pass what? For it to be a process, it needs to pass the first and second law. So we have heat transfer coming in at 100. We have work being produced, 55. So where we should be having QL, 45, the difference between those two, right? And just thinking, well, what about this pump over here, right? What about this pump? Well, you can think, well, maybe this network out, maybe some of it's coming over here, right? Or maybe we have 10 coming around here, and then that's going to be added into here. We're going to have some of it expelled over here. This steam power plant, the condenser is the device where large quantities of waste heat is rejected to rivers, lakes, or the atmosphere. Can we not just take the condenser out of the plant and save all that wasted energy? The answer is, unfortunately, a firm no. For a simple reason that without a heat rejection process in the condenser, the cycle cannot be completed. Okay? Every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized conditions. So, a couple things I don't want to talk about here. Idealized. This is perfect conditions. Perfect. Right? And we know that perfect is never, ever, ever obtainable. Idealized, an example of an idealized condition is a isolated system. not just a closed system, but an isolated system, right? Or we have been operating under idealized conditions all in first Thermo 1 because we did not take into account friction, or we didn't really take into account friction, right? We're definitely having some loss there. Okay, so under idealized conditions, it's perfect conditions. Everything is operating at 100% efficiency. It's wonderful. We still need heat energy waste because we also need to keep the same, right? So if we're starting a boiler at 100 degrees, let's just say for easy math, and we can't capture that because we're not efficient enough to capture that, we're only capturing 50, well, then that 50 is going to go around and go back into a boiler, and then we're going to have some more come in. And then we will start also, number one, under idealized conditions, it'll just get too hot for us to actually generate any usable work there. But also, things happen, and especially if you're using chemicals, some of those chemicals will change with heat as well. So you have to have, and it's a firm no, because I promise you, if there was a way to use any heat rejection, we would. We absolutely would, because it's more efficient and it costs less money, right? So we want to capture everything, but it's a firm no. We definitely cannot. Okay? A heat engine cycle cannot be completed without rejecting some heat. Okay? And so you see here, we've got gas at 30 degrees Celsius, reservoir at 100 degrees Celsius. Heated is going to be 100 degrees kilojoules. It's going to raise up that piston. We're going to need some heat out. Why? Because we can't start from here. If we're here, we need to reject some to bring it back here to complete a cycle. The cycle has to start and end at the same place. Okay? We can't start and end and then somehow get back to the start. We need a cycle. We need to come back. We need to reject. Right? We need to come back to the starting point for a cycle. Net power production of a heat engine. And so here we have some formulas. It's just very easy. 80 minus just the difference, right? And then here's the schematic. We've kind of walked over there. Now, I mentioned it before. Now, we actually use a few statements to better describe the second law of thermodynamics. So let's look at the Kelvin-Planck's statement. It is possible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, it is possible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount, some sort of work. This statement is saying that is possible. Heat engines are possible. No heat engine can have a thermal efficiency of 100%. No heat engine can be 100% efficient. This is saying that we have to expel some. We can't take, within a heat engine, we cannot take 100% of that thermal energy and have the same amount for net work out. We can't do it. Or, as for a power plant to operating, the working fluid must exchange heat with the environment as well as the furnace. We must have some coming out. The impossibility of having 100% efficient heat engine is not due to friction or other dissipative effects. It is a limitation that applies to both the idealized and actual heat engines. So what it's saying is, hey, on top of the fact that we can't have friction, and we're going to have friction, on top of we're going to have some dissipative effects, on top of idealized regions, we can't have it from an actual heat engine. It's not going to function. A heat engine that violates the Kelvin-Planck statement of the second law, it's It's not workable, right? We cannot have a thermal energy reservoir come around and have 100 in and have, 100 out. It's not possible. And if it was possible, think about it. Okay, let's just say it was possible. It would not be a heat engine. It would just be an energy transfer. We wouldn't even have a heat engine. What's the point of a heat engine if you can just have one inlet and one outlet, right? We don't need that. We would absolutely be taking into account 100% of what we can. But we cannot do it. It's a natural law. We're not able to do it. Okay? The transfer of heat from a low temperature medium to a high temperature one requires special devices called refrigerators. We have one. Okay? Refrigerators, like heat engines, are cyclic devices. They just, look here, operate in reverse. The working fluid used in a refrigeration cycle is called the refrigerant. The most frequently used refrigeration cycle is a vapor compression refrigeration cycle. We talked about that a little bit, talked about compressing it to get a chemical change and a drop in temperature. In a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant. Remember I said, hey, don't think of it as blasting cold air in. Think of it as heat absorbed. Heat absorbed, because the first law, remember, flows from hot to cold, not the other way around. The other way around, cold to hot, that violates the second law. We have an arrow of direction right here, hot to cold. Heat is absorbed by the refrigerant, serves as the evaporator, and the coils, usually behind the refrigerator where the heat is dissipated to the kitchen air, serve as the condenser. And so you'll see here, you follow the flow of energy. We have QLN, we have a low heat transfer. We don't have cool air, we have a low heat transfer going into that evaporator. And we're coming around, and we have some network into this compressor because we need to make this non-natural phenomenon work. We need to put some work in there. And then that's going to come up. It's going to be hot. We're going to expel. We're going to absorb that heat and expel it out the back of the refrigerator. And then we're going to come around. We're going to go to an expansion valve. We're going to cause a drop in temperature. We're going to come back around into the refrigeration space and see the evaporator. Okay. Coefficient of performance. The efficiency of a refrigerator is expressed in terms of COP, coefficient of performance. That's where we're going to find how efficient the refrigerator is. So you see we have those formulas here. And you can see the same heat engine schematic, just in reverse, because this is the refrigeration one. So you have QL, a low heat transfer. I'm not going to say cold. I'm going to say low heat transfer because remember, we do not want to violate the first law. We have some network coming in, and then we have QL being expelled. QH being expelled. Okay, we have heat pumps, which is coefficient of performance formulas here. We kind of already talked about those. All right, and then refrigeration and heat pumps. So this is a cold outdoor air, all outdoors, and then warm indoors. And so we have right here, we have some work coming in, and QH coming in. We are heating this house, right? So we have right here, we have a low temperature coming in. We're going to go into this. Around here, we have some network coming in, and we're going to expel that hot discharge into our indoors. We're going to heat this house. Isn't that amazing? Your air conditioner works theoretically, right? I'm not going to say exactly because it's, you don't have a refrigerator hooked up outside, right? But theoretically, and basically the same as your heater. We're just using the expelling to heat indoors. So, of course, there's multiple different types of heaters, but just from a schematic. The work supplied to a heat pump is used to extract energy from the cold outdoors and carry it into the warm indoors. performance of refrigerators, air conditioners, heat pumps. Most heat pumps in operation have a seasonally average coefficient of 2 to 3. Most existing heat pumps use the cold air outside as a heat source in winter. Okay, and then in cold climates, their efficiency drops considerably when temperatures are below the freezing point. That's just because it's harder to work. It's harder to get that into that working fluid because it's colder. You need more work in to convert it, to bring it up. Such cases, geothermal ground source is uses the ground as the heat source, and it can be used. And this is because in really, really cold environments. So say you were in a cave. I did a cave tour a couple months ago. And so it was very, very cold outside. But when you went underground, it was relatively warm. And it's because the temperature is much more stable underground. It's much more consistent. So if it's really, really cold outside, the ground is going to be warmer. Or if it's really, really hot outside, the ground is going to be colder because it's keeping that, I won't say completely, but much more close to equilibrium temperature than what we experience just in our natural atmosphere. Such heat pumps are more expensive to install, but they are also more efficient. It's because it's more stable. That's one reason why it's more stable, right? Air conditioners are basically refrigerators whose refrigerated space is a room or a building instead of a food compartment. The coefficient of performance of a refrigerator decreases with decreasing refrigeration temperature. It is not economical to refrigerate to a lower temperature than is needed. Of course, you need more energy. You need more work in. You don't need to freeze every part of food. That's just making it work harder. Energy efficiency rating, the amount of heat removed from the cooled space in BTUs for 1 watt hour of electricity consumed. So let's move to the second law of thermodynamics, the Clausius statement. So we have the Kelvin-Planck statement. We can't violate that. And now let's look at the other statement. These two statements are the ones that describe the second law. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. It states that a refrigerator cannot operate unless its compressor is driven by an external power source such as an electrical motor. You know what that means? That means that if we have a QL coming in of 5 kilojoules, we can't have zero work to have hot. What does this mean? I can't take something that is a cooler temperature and work it into a higher temperature without putting some amount of work in. That's what it means. This way, the net effect on the surroundings involves the consumption of some energy in form of work, in addition to the transfer of heat from a colder body to a warmer one. So I need both. I need work to come in and do the thing that is not naturally going to happen, which means something is going to go from a lower temperature to a higher temperature on its own. Right? I need something else coming in. To date, no experience has been conducted that contradicts the second law, and this should be taken as sufficient proof of its validity. That is because these are natural laws, remember? Natural laws is not finding the validation that it does exist. It's not finding evidence that it doesn't exist. And that, obviously would not prove its validity if it was something small. But these are like in history, right? In every experiment, in everything that has been done to try and do, and just in life and recorded life, these have not changed, right? And so this is a refrigerator that violates the Clausius statement because you see this is not going to happen. I can't have no work and go all the way over here. If so, why wouldn't I just go here? All right? I can't go from cold to warm. I need something else to come in and do it. So here's the equivalency. of the two statements. This is proof that the violation of the Kelvin-Planck statement leads to the violation of the Clausius statement. You see how they are related but not exactly the same? The Kelvin-Planck and the Clausius statements are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. So this is how we express the second law of thermodynamics, the Kelvin-Planck and the Clausius statement. Any device that violates the Kelvin-Planck statement also violates the Clausius statement, and vice versa. So if you violate one, you violate both. And here they are, right? So if you have QL coming in to a refrigerator, and you have this heat engine, right? You have QH plus QL, high temperature reservoir, going in QH into an heat engine, and now you've entered into the cycle. And then here you go. So you need that work coming in. You need this work coming in, right? Work. You need this, and it's both missing if you violate it. So if you violate one, you violate both. Okay? A perpetual motion machine that violates the first law of thermodynamics. So here you have any device, a perpetual motion machine first, is any device that violates the first law or second law. A device that violates the first law by creating energy is called PMM1, and any device that violates the second law is called PMM2. Perpetual motion machine 1 is first law. Perpetual motion machine 2, PMM2. Okay? And so here, let's follow this flow of energy. So we have boiler coming in, we have heater, we have turbine coming out, network out, and then coming in you have Q, here you go, and then a pump, and then a boiler. And so then you have this generator that's just network out, and then again network out, and then we're coming in and we're trying to heat this resistance heater, and then that's coming out is just network out. It's not generating, it's not receiving, it's not, and it'll make more sense when we actually start working these, but you see the shaft is flowing through all the way to the pump. All right, and so it violates the first law. And this is one that violates the second law, PMM2. Okay, and so you see here it's missing that condenser. There it is. We need something to expel out as well. See, so we have that Q out. Okay, and then reversible processes, a process that can be reversed without leaving any trace on its surroundings. And then irreversible process is a process that is not reversible. So I want you to think of it as rubber band, right? So if you have this rubber band and you stretch, and it goes to this, it's stretched, and when it comes back, it's just back to that rubber band. This is reversible. Okay, irreversible, I want you to take this plank, this like toothpick, let's just say toothpick right here. And then you bend it. And then this toothpick is bent like that. And then you let go of it, and it's going to stay just like this. This is like state 1, state 2, and then state 3. This is a reversible process. This, state 1, state 2, and then state 3. This is irreversible. Okay? All the processes occurring in nature are irreversible. Why are we interested in reversible processes? Because they are easy to analyze, and they serve as idealized models, theoretical limits, to which actual processes can be compared. This is really important to know. So when we talk about reversible processes, we know, just think of it from a common sense standpoint. Even though we're up here and we have this rubber band, and we've stretched it and it came back, is it 100% the exact same as state 1? Is state 1 and state 3 the exact same in real world? Of course not. It's going to have some little fissure, some loss of elasticity. It's going to have, maybe we don't even have the tool to calculate the additional length that we got from stretching it, right? We know in our brain that it's not 100% completely reversible. But we use these types of scenarios to analyze them so that we can get limits. Because we know that if we can calculate a limit on a reversible system, then we're never going to get over that, because that's the best it's ever going to be, right? So that's when we can take this, hey, this is the best you're ever going to get. You're only ever going to get, let's say, a car, right? You're only ever going to go as fast as 500 miles an hour in this newly designed car. It's all you'll ever get, 100% idealized conditions. You're only ever going to get 500 miles an hour. Well, now you can take the actual output or the actual speed and come up with the efficiency of it. Well, compared to what I could be getting, I'm getting really close. This is very efficient. Or, oh, I'm actually not getting any close. Let's make some of the other systems better, right? Some processes are more irreversible than others. We try to approximate reversible processes. Why? So that we can compare them, so that we can see how efficient our item is. Or our process, whatever we're doing, right? Reversible processes deliver the most and consume the least amount of work. Why? Well, because it's under idealized condition. We're going to be extrapolating the most, and we're going to be using the least amount of work, right? Irreversibilities, the factors that cause a process to be irreversible, are called irreversibilities. They include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, right? Electric resistance, inelastic deformation of solids, chemical reactions, right? So many irreversibilities, and more, right? The presence of any of these effects renders a process irreversible. So we know that actually everything is irreversible. But we do use things and assume they are reversible so that we can use them as measuring points. As, even goals, you can think of it as a goal, trying to achieve, reversible levels. You know that you never will, but that's the best that you could ever get. So that's what you strive for. Heat transfer through a temperature difference is called irreversible. And the reverse process is impossible, right? So heat transfer through a temperature difference is irreversible. You can't undo it. And also you can't reverse it as well, right? So we go from hot to cold. And so we can't go backwards and we can't undo it. Internally and externally reversible processes. Internally reversible process, if no irreversibilities occur within the boundaries of the system during a process. Okay, so that's internally reversible process if no irreversibilities occur within the boundaries of a system. Okay, externally reversible is if no irreversibilities occur outside the system boundaries. And then totally reversible process, it involves no irreversibilities within the system or its surroundings. Okay. A totally reversible process involves no heat transfer through a finite temperature difference, no quasi-equilibrium changes, and no friction or other dissipative effects, which we know exist, right? So we know that this is not physically possible, but we will calculate on it. Totally and internally reversible heat transfer processes. So this is just a schematic of that. And then the Carnot cycle. So this is the execution of the Carnot cycle in a closed system. So you have a reversible isothermal expansion. That's from 1 to 2. You can kind of see, maybe if you screech in. So, I'll just do 1. Or I don't want to do 1 because then that might confuse. Let's do A, B, C, and D. Just for your reference. C and D. Well, that definitely looks like a O. Okay, so here We have reversible isothermal expansion. So we have QH going in, so we're going to have some expansion. Okay, and then we have reversible adiabatic expansion. So that's going to be here. Okay, and reversible isothermal compression. So we're compressing. And then we have reversible adiabatic compression. So just showing you on a schematic. Okay, so here's the PV diagram with the process of the Carnot cycle. So you see we've got PV, so these are our T lines, right? And this is again PV with our T lines. And this is a diagram of the reversed Carnot cycle. So you see that it's just going, our arrows are just going in opposite directions. And then our heat transfers reverse for between these two. Okay? The Carnot heat engine cycle is totally reversible. It is a totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. The efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the two reservoirs. So that makes sense, because if it's reversible, then we know, well, if we perceive that it's reversible, then we know that it is operating under idealized conditions. So of course, the efficiency of that is going to be higher, because theoretically, it should be perfect efficiency, right? So the efficiency of an irreversible heat engine is always going to be less. The efficiency of all reversible heat engines operating between the same two reservoirs, so operating under the same conditions, are the same, right? Because if you have the same conditions, and within those two conditions, they are perfect or reversible or idealized, then the efficiency is going to be perfect and thus the same. Proof of the first Carnot principle. So here we have A, and remember we can't violate, right? Can't violate the first or second law of thermo. A reversible and an irreversible heat engine operating between the same two reservoirs. The reversible heat engine is then reversed to run as a refrigerator. Okay, and then B, so that's able to be done, correct? And then B, the equivalent combined system. So all this is saying is that it doesn't violate the first and second law. So it's just letting you know that the Carnot cycle does not violate any sort of law. All reversible heat engines operating between the same two reservoirs have the same efficiency, which is the second Carnot principle, which means that when you have the same conditions and they are reversible, then they're going to have the same efficiency. A temperature scale that is independent of the properties of the substances that are used to measure temperature is called a thermodynamic temperature scale. Such a temperature scale offers great conveniences in thermodynamic calculations, of course, because as you can see and as you have seen, temperature is one of the main, especially with PVT because of the relationship, it's one of the main things that we work with. Okay, and so then here for the schematic, the arrangement of the heat engines used to develop the thermodynamic temperature scale. So this just kind of goes through what those are. And then you can kind of see T2 where it takes, certain temperatures. So you have T1, which is the thermal energy reservoir. And then T2 is about midway through. And then T3 down there is the thermal energy reservoir at the bottom. This temperature scale is called the Kelvin scale. And the temperature on this scale is called absolute temperatures. Okay? And for reversible cycles, the heat transfer ratio, which is QH over QL, can be replaced by the absolute temperature ratio, TH and TL. A conceptual experimental setup to determine thermodynamic temperatures on the Kelvin scale by measuring heat transfers QH and QL. So this is just giving you, so first of all, this T in Celsius equals T Kelvin minus 273.15. Of course, that's the conversion. But then this is just showing you that QH, again, with these boxes, like what is happening? QH over QL, and this is equal to TH over TL. And this is in regard to reversible. Okay, and then here we just have irreversible heat engines. So thermal H less than HTH is reversible. And then if it is equal, it's also reversible, and greater than reversible. And then this is irreversible heat engine, right? Irreversible heat engine. And then this is, reversible heat engine. And then this right here. So the thermal, any heat engine over the Carnot heat engine. So any heat engine being greater than the Carnot heat engine is impossible. Because remember, we are talking about reversibilities within the Carnot heat engine. And so that is the most efficient, right? So having something greater is just not, it's just not possible. And so if you have a heat engine that is, or any heat engine, right? So any heat engine, if you have any heat engine, which is denoted by this, if it is equal to the Carnot heat engine, which we know when we're talking about reversibilities, and we're talking about the Carnot heat engine, so that's how we denote that. If these are equal, then we know that that's a reversible heat engine, right? And if the Carnot heat engine, any heat engine, is less than the Carnot heat engine, well, then we know that that's an irreversible heat engine, and this is what we deal with, right? This is what we deal with, is irreversible heat engines, right? The Carnot heat engine is the most efficient of all heat engines operating between the same high and low temperature reservoirs. And the reason why we say operating between the same, the reason why we have this statement is because if you start changing the parameters of the experiment, right? If you start changing the temperatures between the two things that you are comparing, then you're not comparing equally, right? So we always make that that little plug in there to let you know that, hey, these are tested under the same conditions so that we understand what is able to be operated between the two. No heat engine can have a higher efficiency than a reversible heat engine operating between the same high and low temperatures. We've talked about that, right? So you cannot have a higher efficiency than a reversible heat engine. The Carnot heat engine is the reversible heat engine. Therefore, you cannot have a higher efficiency than the Carnot heat engine. So therefore, if your heat engine is equal to a Carnot heat engine, then you are having a reversible heat engine with the highest efficiency. If your heat engine is less than the Carnot heat engine, well, then you're having a real world, an irreversible heat engine, right? One that we encounter all the time. And if your heat engine, if what you're calculating with your heat engine is a higher efficiency than a Carnot heat engine, well, then you know that's impossible and that's not realistic because you can't have something better than perfect. You can't have more perfect. It's either perfect or not. To say something is more perfect is not even a correct thing. So that's where this comes into play. This is the peak. This is the limit for heat engines. This is just an analysis of the heat engine. Just make sure that you're remembering, right? So this is thermal heat engine, and then when you see reversible, we're talking about Carnot, right? Remember that denotion right there, okay? And so this is just, it's really just plugging in some details there. And then when we start talking about the quality, right? So the quality right here, the efficiency is denoted as a percentage. The fraction of heat that can be converted to work as a function of the source temperature, right? Because we want to look at the efficiency of it. How efficient can we be? How much heat can be converted to work? How much are we able to convert 50% of it? How efficient are we able to do it? What is the quality of this, right? The higher the temperature of the thermal energy, the higher its quality. Okay, so that just, it makes sense because there's how is energy transferred through heat and work. So there's more to use. There's more to be garnered. There's more to grasp. There's more to achieve. So the higher the temperature, the higher the available energy, the higher its quality. So here is any refrigerator or any heat pump, the coefficient of performance of a refrigerator and of a heat pump. That's denoted by R and H right here. Coefficient of performance of a refrigerator, coefficient of performance for a heat pump, and there's the formulas there. And then the Carnot refrigerator or heat pump, coefficient of a refrigerator, reversible Carnot, right here. Remember when you see that you're talking about Carnot, okay? Coefficient of performance of a heat pump, reversible Carnot, right? Okay? No refrigerator can have a higher coefficient of performance than a reversible refrigerator operating between the same temperature limits. Why? Because nothing is going to get better than perfect. And reversible systems, regardless of if it's a refrigerator, regardless of if it's a heat pump, doesn't matter. If something is reversible, it's under idealized conditions. It's under perfect conditions. It's never going to operate better than perfect. It is the peak. It's your upper limit. So here's the coefficient of performance of a refrigerator. Again, if your coefficient of a performance of a refrigerator is less than that of COP refrigerator Carnot, reversible, then that is an irreversible refrigerator. This is what we've got. This is what's in your house. If you have, oh, there's an arrow on this page. Let's see it right here. I'm sure I was going to get emails for that. Rightfully so. Okay, so if you have a coefficient of performance for a refrigerator, and it is equal to the coefficient of performance of a refrigerator for a reversible system, a Carnot system, if those are equal, well, then you have a reversible refrigerator, right? Because you can't be better than the very best. So if a Carnot is reversible, and that is what yours is equaling, then it is also, by proxy, reversible. And then, of course, if the coefficient of performance of a refrigerator is greater than that of the same, but a Carnot, then that's an impossible refrigerator. So we can't have this. Not able to be done. Okay? And so just a note here, the coefficient of performance of a reversible refrigerator or heat pump is the maximum theoretical value. We've talked about that for the specified temperature limits. And then actual refrigerators or heat pumps may approach these values as their designs are improved, but they can never reach them, right? Because we can never get something in perfect conditions. But our goal is not to reach, or our realistic goal, right, is not to reach the perfect conditions. We know we're never going to, but we can improve them. The coefficient of performances of both the refrigerator and the heat pumps decrease as the temperature L decreases. And that is, it requires more work to absorb heat from lower temperature media, right? Because if you have, just think of it like water. If you have a lot of water, it's going to be very easy for you to soak it up. It might take you a really long time, but it's not difficult at all to go out there and start soaking up water from a pool. It's not difficult at all. But if you have a microscopic amount of water inside of a room, it's going to take you a really long time to try and find that water and soak it up. It's the same kind of thing. It requires more work to absorb heat from a lower temperature because it's less to get. It's less readily available. Okay, and then here's some just the Carnot refrigerator and the heat pump in regard to refrigerators, heating your house, things like that, and the formulas here. And there's one worked for the network. Okay, so just in summary, we talked about the second law, we talked about the arrow of time, the Kelvin Planck, and the Clausius' two statements. We talked about thermal energy reservoirs and how they relate to the atmosphere, water, things like that. We talked about heat engines in great detail. Now, we can't have a heat engine that expels all of its work, right? That's a violation of the second law. Refrigerators and heat pumps, we talked about those and how they're essentially just opposite directions, right? Perpetual motion machines, we talked about RPPs and how some may violate the first or second law. And we talked about reversible and irreversible processes where we're going to be calculating them, right? And reversible is the maximum efficiency. It's 100% perfect. And then irreversible is what we actually have. And the ratio of those being compared together is our efficiency. We talked about the Carnot cycle and how we use those to measure our irreversible processes too, and the principles that go along with that. We talked about the thermodynamic temperature scale, Kelvin, and how we use those to measure, right? And we talked about the Carnot heat engine as well as the Carnot refrigerator and heat pump. So we talked about all of those and how we use them, greater than, equal to, less than. We talked about all of these. So hopefully when we're going through and working them and you start getting data, then you'll start understanding how these relate to real world applications.